Hello, everybody. So we are going to get started. This is IAS Distinguished Lecture by Professor Randall KAMIEN from University of Pennsylvania. So I have his bio here. Professor KAMIEN received his PhD in physics from Harvard University. Then he stayed in Institute for Advanced Study at Princeton as a member, and afterwards he moved to University of Pennsylvania, right? Am I right? Yes. Okay. So right now he's a Vicki and William Abrams Professor in Natural Sciences. Professor KAMIEN receives a lot of awards, including G.W. Gray Medal from British Liquid Crystal Society in 2016. He was also elected as a Simmons Investigator in 2013. He also is a Fellow of the American Association for the Advancement of Science in 2003, and a Fellow of American of Physical Society in 2001. He's also a chief editor, lead editor of reviews of modern physics. So now let's welcome Professor KAMIEN to give us the lecture on the softest crystals. Okay.
Hi, thank you. Thank you for having me. The weather's perfect. The weather's been perfect. It was cool yesterday and sunny today. So I'm going to tell you about these very soft crystals. And when I say crystal, I mean liquid crystal, but it's a crystal. I'll show it to you. And it's very soft, and it means it can do things that normal crystals don't do. In particular, if you take this kind of liquid crystal that I'm going to talk about, it's called a smectic, and you pour it into a test tube, and you just let it relax, this is what you see. And these patterns, these are ellipses. These are perfect ellipses. And these black spots are exactly at the foci of the ellipses, right? I don't know, yeah, foci of the ellipses. And sometimes when you look really carefully, you can actually see that there are parabolas and hyperbolas in here too. They're perfect conic sections. So the material has some sort of internal structure, which you can't see in this regular microscope picture. The molecules are only maybe a nanometer long. The structure is on the nanometer scale. But on the optical scale, you can see something that's giving away that there's an internal structure. By the time we're done, I hope I'll explain this. I hope you'll be able to understand exactly what you're seeing. So not everybody knows about liquid crystals, even though they're $100 billion a year industry, 100 billion US, right? US a year industry for displays. Liquid crystals were discovered actually in the 1880s by this guy, Reinitzer, and then Otto Lehmann helped categorize them. And all these guys back then, they're all classically trained, so they all knew Greek and Latin, and so they gave them names that were all Greek names, right? Because that's what they knew, that's how they labeled everything. It was like the animals, except it was Greek. So what's a liquid crystal? A liquid crystal is something that usually you think of it as made of rods. You don't have to think of them rods. They could be discs. But you can have rods. And so what's special about rods? If you throw rods down on the ground, or you, right, you know that there's a game, pick up sticks. Do you guys play it? You know, pick up sticks. Okay, right? You throw all the rods down on the ground. Not only are they randomly placed, they're also randomly oriented. And what's special about that is that it's a liquid from the point of view of the centers of the rods. If you just looked at the centers, you'd say, oh, there's no order. It's not a crystal. There's no lattice. There's no symmetry. There's no structure. But it's also random in terms of the orientation. Spheres don't have that property. When Elong studies colloidal crystals, right, his colloids are spheres, right? Aren't they? Yes. You want them to be spheres, right? And so they're spheres. The spheres don't get to have this extra degree of freedom telling you which way they're pointing. But these rods do. And so you can actually concentrate the rods and you can get them to line up into this phase called a pneumatic phase. They line up, but they're still not a crystal. They're a liquid, right? So they're still liquid if you look at the centers, except they're all pointing in the same way. That's how you win in pickup sticks, right? You grab lots of sticks, and when you grab them, they're all pointing the same way. But it's not that ordered. Eventually, it gets more ordered when you buy a box of pencils, right? The pencils are all neatly stacked inside there. But if you're just grabbing a bunch of sticks or a bunch of French fries or a bunch of, any kind of thing that's stick-like, usually they all point in the same direction, but they still are not making a crystal. And so what does that mean? Why would I call it a liquid crystal? Well, it's a liquid because if I take the top and I shear it, if I make shear, it just flows, right? It's like a swimming pool. When you push the top of a swimming pool slowly, the bottom doesn't respond, okay? It's not true in a solid. In a solid, if you push the top of a solid, the whole thing moves, right? It supports shear. But a pneumatic has this funny property. Suppose this room were filled with pneumatic, and I took the rod over here and I gave it a twist. Well, that means that the rod over there would also want to twist because they all want to point in the same direction. So that means I can transmit a torque across the room. I can do this, and I can send a torque across the room. I can't send shear, but I can send torque. Now that's something a crystal does too. If you take the top of a crystal and you twist it, the bottom twists also. So a full-blown crystal, the solid, a block, that gets to transmit shears and torques. But this liquid crystal transmits torque, just like a solid, but does not transmit shear, just like a liquid. In fact, it doesn't even transmit torque in all directions, because if I took the top rod and twisted it, it wouldn't know anything, right? So it doesn't even transmit torque from top to bottom. It only transmits torque sideways, all right? And so the idea here is every time a symmetry is lost, so this phase has rotational symmetry and translational symmetry. This one lacks rotational symmetry. When you lose a symmetry, you get a way of transmitting long-range somethings, torques, shears, whatever. Okay. You don't have to have rods. You can have these things, these plates. Plates would also do this. In fact, when you do, what's that called? Xeroxing? You know Xeroxing? Xeroxing? You copy paper, you put it in the machine, you make a Xerox, right? Xerography is based on molecules like this. So are laser printers. Discotic molecules, which all, instead of orienting their long way, they orient their short way. So the normals to the layers are all pointing the same direction. This is what happens if you throw down a bunch of cards. We have this other game called 52 card pickup. Do you play this game? Your daughter might like this game because you throw the cards on the floor and they all land randomly, but they're all oriented the same way. Okay, and so you can have this kind of order. All of these things transmit torque. This doesn't transmit anything. The material I'm eventually going to tell you about is this material called Smectic A. It is a crystal, but it's a crystal in only one direction. It's like the floors of a building, right? In a building with an open floor plan, each floor is a certain spacing apart, but then where the desks are is random, okay? And so a smectic has layers. Each layer is a fluid. Each layer does not transmit any shear. But the layers are all stacked up. So I can transmit a special shear. I could push this side of the smectic up, and that side will also move up. But if I slide the top, the bottom doesn't move. So I can transmit some shears and some torques, but not all shears and not all torques. That's why it's not a crystal, but it's also not a liquid. So it's not a bad name to be in between, right? It has both properties of liquids and crystals. And of course, I want to show you this again. No. Okay. This is not really what the molecules look like. I mean, they're molecules. They have like carbon and nitrogen and hydrogen and stuff like that. They're little molecules, all right? And what do they actually look like to us, all right? Because you can't see the molecules, right? And these guys definitely couldn't see the molecules. The guys in 1888 couldn't see them. This is what they saw. So they took some material and they said, look, you see these lines, these dark lines? Well, the Greek word for line is pneuma. So they called it the pneumatic phase. There it is, it's the pneumatic phase. Okay? And here they got this picture. This is DNA. You know, DNA, the DNA we know. And the DNA here, when you look at the picture, you get all these different colors. This is called a greasy smear, which is a good name for it. But it tells you something. You see how you're getting colors reflected back, how it's a little opalescent, how different colors reflect. This is under white light. All right? That means that there must be some sort of Bragg planes in there. Right? Because they're reflecting light. It's diffracting light back at you in different colors. And these Bragg planes must be ordered in some funny direction. So there's a lot of information you can get just from looking at the optical picture, which is, 4 orders of magnitude, 5 orders of magnitude bigger than the size of the molecules. Right? This picture is probably 100 microns, maybe even more, maybe a whole millimeter across. Here's another picture. This is a cholesteric phase. I know it looks like a brain. It looks like fingerprints. So here you have this pattern, which is periodic. Okay? And you see the periodicity? What's the periodicity of this? Anybody? I'm going to ask questions. I'm going to ask Elon because I know him. I'm going to pick on him. What do you think the periodicity is? No, exactly. This is about a micron because I can see it in a microscope. No, the spacing, the micron spacing has nothing to do with the cell thickness. Somehow these nanometer scale molecules collaborate to make micron scale patterns. So it's kind of an amazing thing. Not only is there a difference in length scales between what you can see optically and the size of the molecules, they actually make length scales that are visible, which is one of the reasons why they're so useful in displays. Here's another one where, again, you get stripes that are on the scale of a micron. And I know that you're finding these pictures colorful. I'm going to explain them in a second. This is called the blue phase, for obvious reasons. This material, I know you think it's a crystal. See, it looks like it's a crystal. It has facets and all that. But here's the cool thing. It's not a crystal. It's a liquid crystal. Crystals are things that have three-dimensional periodic order. You know where the molecules sit. This has three-dimensional orientational order. At each point in this blob, the molecules know which way to point in 3D. And there's a periodic pattern of pointing. And the period's about the color of blue light. The period's about, 500 nanometers. But this thing flows. Stuff just flows from one side to the other. Right? It does not support shear. It supports torques in all 3 directions, but no shear. And eventually I'm going to tell you about these. These are smectics. And one of the nice things about this topic is that the pictures are quite colorful and beautiful. This is not artificial color. This is just what you see under a microscope. And it turns out the people who are really expert at, this is called a smectic phase. How do I know it's a smectic phase? Because somebody told me it's a smectic phase. How do they know? Because have you ever baked? Have you ever cooked something? Have you ever cooked something, Elon? Never? Okay. All right. Well, then I'll have to stop. So sometimes when you bake things, there's a stage where it says, beat the egg whites until they're stiff. Soft peaks, hard peaks, this kind of peak, okay? Boil the syrup until you get, hard crack, soft crack. They give you some sort of language. It turns out when chemists are doing synthesis, sometimes the intermediate state is a liquid crystal. So they say, cook it. And if you want to make sure that this stage, that you're in stage 4 and you're in the right material, put a drop of it under the microscope and look at it. If you see the smectic focal conic fan-like texture, then you have the right material. So it's like stiff peaks. Okay, so for them, this is a way of quickly identifying, do they have the right material? Okay. So what were you looking at? So here's a picture. I guess I pulled it off the internet, right? Of this pneumatic phase. And you see the lines, right? And so they know, here are the black lines. You have a pneumatic. What are you actually seeing? Well, you look at it. You say, well, there are these black lines, but then they end in these crosses of 4. And sometimes they end in pairs. Sometimes you have these 2 black lines that come together in a pair. What are you looking at? So here's the whole experiment. This is the whole basis of the display system also. You have a backlight, you have a polarizer, and you have a second polarizer, which is 90 degrees from the first polarizer, which we'll call the analyzer so we don't get confused, all right? If you send light through here, nothing happens. All that you get out is black. Nothing goes through because the polarizer polarizes light this way and the analyzer can't find any light in its direction. But if you put liquid crystals in between, the liquid crystals are birefringent. They have a different dielectric constant for waves that are parallel to the long axis and perpendicular to the long axis. So what happens? Light comes through the polarizer. It gets split into the orientation, into the directions, the extraordinary and the ordinary direction of the molecules. So there's a component this way and a component this way. And one of them moves faster than the other because the dielectric constants are different. And by the time you get over here, the polarization has rotated. And so you actually get light out. So when you put the little crystal in there, light goes through. The only time when light wouldn't go through is if it turns out that the molecule is along the polarizer direction. Because if the molecule is along the polarizer direction, polarized light comes through, you only have one wave. You only have the ordinary wave. And it goes through, and there's no mixing, there's no phase delay, and what comes out is polarized. Also, if it's along the analyzer direction. And so when you look at the picture, what you're seeing is you're seeing black lines. That's wherever the molecule is pointing along the polarizer or the analyzer. And everywhere else, it's not pointing along the polarizer or the analyzer. Okay? By the way, if you use an electric field, which are easy to make, and you rotate the molecules so they're no longer lying in the plane of the polarizers, but they're pointing from the front to the back, now there is no dielectric anisotropy, and now you always get black. So if you have an electric field, you can switch a thing from pointing like this out of the board, where you get black, to pointing back in the plane, where you get light. That's how a pixel works on an LCD display. That's it. Okay. So why do we get these crosses? What's happening here? You have these black lines. These black lines are places where we're along the polarizer direction, or maybe we're along the analyzer direction. Where they intersect is a place where you don't know which way they point. So let me give you an example. Here, I have my rods. I drew them as lines. And I have a defect here. I have a place in the middle where you can't see, or you don't know which way the molecule points. It's like the origin in polar coordinates. In polar coordinates, you don't know what the angle is at the origin. And this is a defect. But when you go all the way around the defect, the molecules rotate by 2 pi. You go around once, and they go around by 2 pi. Or maybe they go around backwards by 2 pi. But it doesn't matter. When you come all the way around, the molecule has to be pointing in one direction. So it must have rotated by 2 pi, or 4 pi, or minus 2 pi, or something. What would you see under cross polarizers here? Right? If you put this between cross polarizers, I get black whenever the molecules are along the polarizer, or whenever they're along the analyzer. I get 4 brushes that all intersect at one point. They intersect at the place where you don't know which way they're pointing. One set of black lines is polarizer, one set of black lines is analyzer, and they intersect. Where they intersect, you don't know which way the molecules point. They point in no direction. Here's another texture where instead of having this kind of funny kind of shear mode, you have something where things are rotating around in a circle. Okay? Right? This whole vertical line is along the analyzer direction. It'll give me black. And then there's some kind of curve here where I'm going to get things along the polarizer direction, and I get 4. And I get 4 there, and I get 4 there. Why do I get 4? Because as I go around 2 pi, I start in the polarizer direction, black, 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 and I come back to where I started. If I go around by 2 pi, I have to go through 4 brushes. Polarizer twice, analyzer twice. So what about these? Where instead of having 4 brushes coming to a point, I have 2. If I only have 2 brushes, it must mean that I go through the polarizer direction and the analyzer direction, and I come back to where I started. Which means that the molecules don't care which way they're pointing. Just like I drew those rods. The molecules are not arrows. They're not vectors like in a magnetic field. They're actually sticks, just like pickup sticks. They don't have a top or a bottom. Does that make sense? So that means that the molecules have a symmetry, an up-down symmetry, or the phase has that symmetry. And I can see that by looking under cross polarizers. To me, this is kind of an amazing thing. The molecules are a nanometer big. And by looking at this texture under cross polarizers on a scale of a millimeter, I can actually tell you that the molecules or the phase have this up-down symmetry. So that's cool. Topology is really powerful, that I can tell you about the symmetry of the phase just by looking at the class of the defects that there are. You can have higher charges, right? What do? How do I decide this is 2 pi? I count the number of brushes. There's 4 brushes. Each time I go through a brush, I've rotated by pi on 2. So 4 times pi on 2 is 2 pi. And so it rotates around by 2 pi. Here, there are 2 brushes. It rotates around by pi and comes back to where it started. You can have more complicated ones. Here is one where there are 6 brushes coming out. Here's one where there's 8 brushes coming out. 10 brushes, 12 brushes. You can count them. And what's cool about this is I don't have to look very carefully. I don't have to have atomistic detail or nanometer detail. I can go at the length scale of this picture, which is millimeters, and I can just count the number of brushes. And just using this simple fact that I get a brush every time I go through a polarizer or an analyzer, I can tell you the charge of the defect. So that's powerful because I don't have to know about molecules. And you have to remember that all these phases were classified in 1888. Some of them were classified in 1888. They appreciated what they were looking at without being able to see the molecules. I'm not even sure if they knew molecules existed. They must have known in 1888 that molecules existed. But, I mean, it's a place where you can't tell me which way the molecule's pointing. So right here, right? If I come in this way, it looks like the molecule should be pointing up. If I come in this way, it should be pointing this way. If I come in this way like this. So there's no, I can't tell you what the orientation is right here. That's correct. It's a topological defect. I can't get rid of it either, because when I go all the way around out here, the winding is 2 pi, right? And as I continuously deform the structure, I can't change that winding. That changes smoothly. Does it make sense? It's the same as a physical defect in a crystal. I'll convince you.
Well, I mean, physical defect, we can say the bond in silicon, we can say that.
Yeah. Okay, so you're thinking about inclusions, defects like that. I'm talking about things like dislocations and disclinations, which is a different kind of defect. They're topological, right? I don't mean that there's a different kind of molecule there. I mean, it's a place where the order isn't defined. Oh, now we have to go through this again. Okay. But now, I'm not going to tell you about pneumatics. That was the warm-up. I'm going to tell you about these smectic materials. Smectics are very common. Smectic materials are made, for instance, out of these things called amphiphiles. These are molecules with charged heads and oily tails. Your cells, you're filled with them. Every cell wall is made of this, right? So you're filled with this stuff. And you can imagine what happens. The charged heads like water. The oily tails hate water. You throw this in water, and what they do is they make sandwiches. So the charged heads stay in contact with the water, and the oily tails stay in contact with each other. And this shields the oily part from the water and makes all the charged parts happy. And you can dilute the thing by adding water, and the layers get further apart. If you dilute them so much that there isn't even enough space, there isn't even enough stuff for a layer, they'll form a sphere. they'll form a double layered sphere. That's like a cell, right? Where the inside, it's a double layer, there's charged heads pointing in and charged heads pointing out, and there's this oily shell. And I know you're looking, there's an energy here. Physicists always have this thing about writing down energies, right? Because I think that's what most of physics is about. At least freshman physics seems to be about energy. Is that true? You're teaching it now. Energy is a key concept. Okay, good. I don't really want to talk about the energy. I want to tell you how I describe the phase. So the way I'm going to describe this material and the layers is I'm going to write down a field, phi. It's like a potential, like electromagnetic potential. And I'm going to tell you that wherever phi is 0, that's where the first layer is. And wherever phi is equal to A, or where phi is equal to A, that's the next layer. And phi equals 2A is the next layer. You know what's great about this? The layers don't intersect. Right? If I have a function that's well behaved, and I say, here's phi equals 0, that's going to be a surface, and here's phi equals A, and that's another surface, and phi equals 2A is the third surface, and you get these different layers. And if I want to reconstruct the density, all I have to do is take cosine of the phase. Yeah, there's some conversion between A and 2 pi. So you can see here that wherever there's a layer, that's a density maximum. Right? Whenever phi is 0 or A or 2A or 3A, you get a density maximum. And otherwise, you have not a density maximum. I can write down the normal to the surface because grad phi is perpendicular to the equipotentials. And I can normalize it to make it a unit vector n. And then I can write down some energy. And if you look in Landau and Lifshitz, or Landau, that's the only book I know, right? You can look at Landau and Lifshitz. You can see, this is the energy they write down. But the energy has two terms. All that's important is that the layers want to be equally spaced. So that means the gradient of phi wants to be magnitude 1. And the layers don't like to bend. So the divergence of their normal is their curvature. So they want to be flat, and they want to be equally spaced. And that's the ground state, right? And you all know that this is like a deep way of saying Goldstone's theorem. The fact that they make a material with a strict spacing means there must be an energy cost to not having that strict spacing, right? And that's this term here. So you have these layers. I'm going to describe them by this phase field phi. And there's a problem. We wanted to study smectics. They're, slightly more interested in the pneumatics. But there was this theorem. And it was a theorem that was proven by a mathematician, a real mathematician and a real math proof. And I even met the mathematician. So, he's a real person, right? And he proved this. And I could read this to you. You could read it to you. There's very few things in this that we really understood. We understood less than or equal to 1. Okay, and we, a field of directors in R2 with an isolated singularity, blah, blah, blah. What his theorem said, to our surprise, was you can have layers, and if you have a layered system, this is a smectic, layers. You can have perfect layers. You can have a building that's okay. You can have this. This is like, does anyone ever remember, do they have newspapers here? Newspapers? Have you ever seen a newspaper? You've never seen a newspaper? Yeah, okay. Have everyone seen like a museum, a newspaper? Yeah, and they're folded over. Okay, they're big and they're folded over. And on Sunday, they put like ads in the middle, right? And they slide the ads in, okay? And you pick it up and the ads fall out. And this is a defect. Because if I look at the normal to the surface, it's pointing up here. And as I go all the way around, it's pointing down. And the only reason that this line is okay is because up and down are the same. See, if I don't show you this, I can't block it. But if I just show you this part, the part on the right, it looks just like this. But there's a place right here where I don't know which way the layer points. Here I can have a bullseye. I can roll it up into a tube, right? Like a cake. I can also have things that rotate in the wrong direction. So what I mean by wrong, watch the pointer. as I go around this central point counterclockwise, my pointer rotated around clockwise. Here, if I go around counterclockwise, it also rotates counterclockwise. So the direction rotates in the same direction I'm going. Here it rotates in the opposite direction. So we could call this minus 2 pi. Plus 2 pi, plus pi, nothing. This is minus pi, minus 2 pi, minus 3 pi. It turns out what Ponaro's theorem says is that if you have layers, you can do anything you want. You can go to minus 58 pi. You can have any negative one you like. But Ponaro, this less than or equal to 1 means you can't have anything that has charge 3 pi. There's no structure that has charge 3 pi or charge 4 pi. As is purely a topological result. And this was really disturbing to us because we all grew up learning about pneumatics. And in a pneumatic, all you need to do is count the number of brushes. And I showed you that pneumatics have charges that are higher. They have 3 pi and 4 pi. You can bring 2 plus 1 or 2 pi defects in a pneumatic together and get a 4 pi defect. That's allowed. It would look like a dipole. If you looked at the lines, it would look like a dipole in electromagnetism. But for some reason in a smectic, you can't do this. For the, let me just say a mathematical thing. Topological defects are supposed to be characterized by members of a group. And the thing about a group is that if you multiply 2 things together in a group, you get another member of a group. And this doesn't have that property. So these defects in smectics actually don't have a group structure. So that's bad because, if you learn about topological defects, there's this whole homotopy theory of defects, and you're supposed to have groups, and you don't have a group. And this kind of bothered us. This was known to the ancients that this was a problem, but there was no real resolution. Just knowing that it didn't work. So we thought about it, and I worked with Brian Chen and Gareth Alexander on this. And we said, well, let's go back to 2D. Because in 2D, the theorem's that was a 2-dimensional theorem, by the way. Right? And so let's look at 2D. So here is my 2D plane, the xy plane. And here's phi. Now, when you do electromagnetism, when you teach it, you don't usually plot phi like this. Usually what you do is you draw equipotentials. Right? You draw, this is phi of xy equals 0. This is phi of xy equals 2. This is voltage 0. This is voltage 2. This is voltage 7. Right? But I'm going to draw it as a surface living over the xy plane. And I'm going to draw a level set. You ready? Phi equals 0 is when this green surface intersects the plane phi equals 0. Phi is in the up direction. And then I project it onto the xy plane. This is the equipotential phi equals 0. Okay? Then I can take the layer phi equals 1. That's another level set. And I can project it. So this is the equipotential phi equals 1. This is phi equals 0. And so forth. So you see, if you draw these things, these are the smectic layers. They are the level sets of this green surface. It's a topographical map, right? When you go hiking, you get a topographical map. This is like 100 feet, 200 feet, 300 feet, 400 feet. See how much better the English system is than the metric system? Because if it were in metric, this would be like, 31 meters and 62 meters. It wouldn't be nice round numbers, right? But when you have in feet, it's nice. And you have these level sets. And this is just the same thing as a topographical map. So here's a topographical map. Everyone get this? Every smectic is a topographical map because you have these layers. The layers can't touch. That's true in a topographical map also. 500 feet and 600 feet never cross. Right? And what's special about a topographical map? How do you know that you got to the top? There's no singularity in the map. She's right. what you get is a singularity in the gradient, right? The top of the mountain is a place where you don't know which way is down. All directions are down. Everywhere else on the mountain, you know which way is down, right? But there's a point here where every way is down. Another way of saying it is that if you look around, everything's below you. It means that at the top of a mountain, you have a contour line that's a circle that goes around you. And as Sherry said, that's the same thing as having a defect. Because if I look at the orientation of the layer normal, it goes around by 2 pi. So you have this defect that goes by 2 pi. These are the +1 defects. These rotate the same way around as those bullseyes. Here's a bullseye, here's a bullseye. If I didn't give you heights, you wouldn't know if these were lakes, bottoms of lakes, or tops of mountains, but it wouldn't matter. But when you go hiking, okay, some people, when they go hiking, they want to get to the top. But some people, when they go hiking, they want to go from here to here. And they want to go over this pass. And there's this theorem called the mountain pass theorem, which is a general theorem in Morse theory, that says between 2 peaks, there's always a pass. You knew that. It's like a calculus thing. And so, how come I can't have 2 peaks, right? How come I can't take this +2 pi and this +2 pi and add them together? Because if I try to bring them together, I entrain a saddle in between. And the saddle is exactly a place where I rotate around by -2 pi. So it's not that mountaintops and lake bottoms are opposite of each other. Mountaintops and lake bottoms look exactly the same on a topographical map. It's the passes that look different. And if I try to bring 2 mountains together or 2 lakes or even a mountain and a lake together, I have to entrain a pass in between them. And if I have to entrain a pass, the pass cancels one of the mountains. Another way of saying it is if you put a mountain on top of a mountain, it's just a mountain, right? You can't do anything, right? There's no way to make it's taller mountain, right? But it's still just a mountain, okay? But when you bring a pass with a mountain, you can annihilate the two. You can destroy a mountain by having it eat a pass, all right? And so the reason that you can't keep going up is because every time you try to bring 2 mountains together, you always pull a pass in together. But I'm going to see if Professor Cohn knows this place. You can have a pass, however. You can combine passes. You know the place? Electric Pass near Aspen is a place where there are 3 valleys. Most passes, you stand at the pass, and there's 2 mountains up, and there's 2 valleys down. But at Electric Pass, there's 3 valleys. There's no reason why you can't have that. You can have 3 mountains around you, and it could be possible. Usually, generically, there'll be a pass between these 2 mountains and a pass between these 2 mountains. But it's possible to have one very singular pass, which has 3 ways down. You can even have a way to have 48 different passes, 48 valleys. You can have 48 mountains around you completely symmetrically, and you could stand in the middle at this very, very sharp pass, because if you slip just a little bit, right, you'll either be going down or be going up. Very, very rough, ragged pass. But you can have 48 valleys and 48 mountains surrounding one pass. You can have any negative charge you like, but you can't have any positive charge. Passes can be combined, but mountains can't. And that is how we understood the theorem. All right? And this is all using this language of Morse theory, and then you can prove everything. And let's go back then to the thing I told you, right? This is telling me, usually, when you study topological defects, and here I'm going to define defects precisely, you have your sample, you have a hole where you don't know something, where the order parameter is messed up, and what you do is you take a path in the sample, you then map this path to a path on the state of ground, the manifold of ground states. These are all the different ways something can point. In pneumatic, In 2D, the ground state manifold is all directions. In a smectic, it's directions and shifts. And when there's a handle here, this is a topological defect. If this red loop maps to a red loop here that I can't contract and pull off the surface, then this is topologically protected. It's forced to be there. And if you're fancy, you can talk about maps from fundamental groups to fundamental groups, but smectics don't enjoy this. Smectics are different. But you can use Morse theory to understand them. But smectics have another kind of defect, which I don't know, I can't tell. I went around the main building here, you know, that building down the hill. I don't know if it's like this or not, but there are certainly buildings in the US that are like this. There are buildings in the US which half of the building was built like in 1931. And they have really big floors, right? There's lots of space between the floors. And then the other half of the building was built in 1953, where because of improvements in technology or shorter people, they made the floors closer together. I'm not quite sure what it is. And so they attach a building with 3 stories to a building with 4 stories, right? Almost every hospital in the United States is like this, all right? And you attach these old buildings to these new buildings, and what do? You have this problem. You start labeling them. I'm going to label them US style. This is the first floor, second floor, third floor, okay? What do you do here? You go in the building on the first floor, right? And you're feeling athletic, so you actually walk up to the third floor, right? You walk up to the third floor, and you're chatting with your colleague, and you're chatting, you're talking, and you go over here to get coffee. The coffee machine's over here. And then you try to take the elevator down, or you walk down, and you walk down 2 floors, because you counted when you went up that I went up 2 stories, so I go back 2 stories. And you find out you can't get out. You look out the window, and you're above ground. What do you do? Right? And you look around, and you say, oh, this is the mezzanine. Right? They always call that extra floor the mezzanine. Right? So they'll say, this is the first floor, this is the second floor, this is the third floor, and they'll add this extra half floor called the mezzanine, which means like half floor or something. Okay? And so what you found is there's a defect. This is a dislocation. You went up 2 floors, you went down 2 floors, but you don't end up on the same floor you started. You have been dislocated. You can have dislocations where you add 1 extra floor. You can also have ones where you add 2 extra floors. And you can add 2 extra floors either by taking a floor and folding it over and shoving it in, or you can do it here where you just have this like pitchfork. This is much less common. We're going to have to wait until the far future when we connect buildings built in the 30s to buildings built in the 50s to buildings built even later where the floors are even shorter. Okay, someday that'll happen. Sometimes we say this is a pre-war building and this is a post-war building, so I guess we'll have to have another war, another world war before you see that problem. So, no big rush. So why is this a problem for smectics, or at least for the language that I told you? Remember I showed you the topographical map? I saw people up here nodding. I said, 300 feet, I actually said 500 feet and 600 feet never cross. And somebody up there nodded. It was you. You're nodding again, okay? But here, the layers cross. Over here, if I were going up the mountain here, this would be 0 feet, 100 feet, 200 feet, 300 feet. But here it'd be 0 feet, 100 feet, 200 feet. And there's some kind of mishmash here. Everywhere else, I can tell you exactly how high I am. Right? When I'm on the old part of the building, I can tell you what floor I'm on. And when I'm in the new part of the building, I can tell you what floor I'm on. But if I'm right here, I can't tell you what floor I'm on. This happens all the time in parking garages, right? You think you don't remember. You're the 3rd floor or the 4th floor. It's complicated. So how do I make this work with topographical maps? And I'd ask you, what kind of map or what kind of mountain has a topographical map that looks like that? Okay, here's a hint. If I start here and go around this loop and I count how high I am, I've gone up 1 floor. So the mountain would have to look like this. It would have to look like a helicoid. That's okay. It's okay, because what I'm going to do is I'm going to say something that I should have said in the first place. Do you remember how I told you the density was cosine phi? There was a 2 pi and an a, but who cares? Remember cosine phi? That means that phi and phi plus 1 are the same. Or phi and phi plus 2 pi are the same. Or phi and phi plus a are the same. In fact, when I tell you the floors and the density of the smectic, I can't tell you the absolute floor. I can only tell you the phase. Right? The density, this phi, does not live on the real line. It lives on a circle. Once phi goes around by 2 pi, it's back to where I started. So you see, this is periodic. This works perfectly. If I go up, here, what I'm saying is 0 feet and 1,000 feet are the same. And 1,000 feet and 2,000 feet are the same. 100 feet and 200 feet are different. But 1,100 and 100 are the same. So there's a periodicity. Inside the periods, I can tell what I'm doing. But then once I go more than one period, I can't tell. If I take this and I add it to the ground state. See, here's the ground state. The ground state of a smectic is layers that are equally spaced and straight, not bent. And if you think about it, that means that the ground state is something where you have a plane at a constant angle. Okay? Does everyone see that? So I'm going to take my helicoid and I'm going to stretch it so that it has the right boundary conditions. So way out here, this attaches to a set of planes out here, right? And that attaches to planes over there, and the planes are exactly at 45 degrees. And you see that this funny twisted helicoid is periodic. If I go straight up by exactly 1,000 feet, I get back to the helicoid again. Now watch this. Now I'm going to take level sets just for you. All right, here is the helicoid. And I take a level set. So far, not interesting. I just get that black line. And I keep coming down. Watch it. See? I get a dislocation. Right? If you take a helicoid that's been stretched this way, so it has a topological defect. When you go around once, you go up in this phi space. But you never draw the phi space. Nobody ever thinks about the phi space when you do electromagnetism. Right? You always draw level sets, equipotentials. But here, I take a cut, and it's a topological defect in the 2D system. So if I'm allowed to have, oh, here's the other one, right? If I'm allowed to have periodic structures, then I can actually have a topographical map on a periodic Earth, right? So once you've got to 1,000 feet, you start up at the beginning again. And that lets me have disclinations. That's places where I don't know which way I'm pointing. And dislocations, those are places where I don't know how high I am. And I can have them both in the same map. I can prove a little theorem from this. It's a nice theorem. It's a pure thought theorem. Suppose that I want to have something where the spacing is uniform. Constant spacing. I don't worry about bending, just constant spacing. If I want to have constant spacing, it means that I want to have my layers, the slope, be exactly 45 degrees everywhere. Although 45 degrees is just units. I'll show you later. Right? I want them to be 45 degrees everywhere. And that means that the layers, that implies that the Gaussian curvature of these layers, of this green surface, has to be 0. And there's only 3 ways of building things that are constant angle. There's this, 2 cones, or half a cone attached to this X, or the flat plane. And these are the 3 kinds of defects. It turns out, this is a quick proof, that if you have point defects, the only ones that can have equal spacing, no compression, is +1, +1/2, and nothing. Otherwise, you have to have compression. It turns out there's one more surface, which I want to show you. It's called Nister's surface because this is her paper. We found this paper. And so this is what happens if you try to take a strip of paper and twist it around into a cone. right? And you always get this funny thing. You can't exactly twist it into a cone or into a helix because there's going to be a hole down the middle. Let me show you. If I take a section of it, I get this nice spiral. And this spiral is actually equally spaced. The distance from here to here, and the distance from here to here, and the distance from here to here is constant. And let me just show you what this is. This is called a developable surface. This is something that's made out of something with no Gaussian curvature. This is about to be called an involute. Let me tell you about involutes. So here I have a circle. And what I do is I draw 4 lines. Oh, these are 5 lines. 5 lines tangent to the circle. And then what I do is I trace out curves that are everywhere perpendicular to those lines. Now let me remind you that dogs can do this. In fact, dogs do this all the time, right? If you tie your dog to a tree, right, the dog will always want to be at the end of the cord. And as the dog tries to roam around to chase something, it will wind itself around the tree. And because this leash is always straight and tangent to the tree, whenever you move, because the leash can't stretch, you always have to move perpendicular to it. And so this will trace out a set of spirals, all which are equally spaced. These are called involutes. Does anybody here own an involute? Let me see. Nobody? You own an involute? No, you don't even own a car. You? You might. I don't know. It's hard to know. Let me show you where you see involutes. You might ask yourself, how do gears mesh? This is a problem that was solved, again, a long time ago. You have these 2 gears, and they're rotating past each other, and you have the teeth. What are those called? Teeth. Maybe they're called, are they called cogs? They're sprockets. No, they're cogs. I can't remember. Okay? Whatever they are, you want that as the gear rotates through the other gear, that there's no slipping. You want these 2 faces to roll on each other. So that there's no slipping, there's no friction, there's no wearing. And if you think about it, if you look at this blue line, this curve that's coming out is exactly tracing out an involute. And what's really cool about this is that if you start with 2 gears that aren't involutes, eventually they'll be involutes. They'll grind themselves away until they just roll without slipping. And if you go, one of the fun things to do, but everybody thinks you're crazy, is you go to one of those cog trains in like Germany or Switzerland, and you go and you look underneath the train to look at the shapes of the gears. The engineers who built it knew this. They figured it out by themselves, right? They didn't let it grind away. They actually cut them in this shape. It also has this nice property that the force is always in the same direction between the 2 gears. So, remember I promised you at the beginning that I was going to explain these ellipses? Here's a picture. This is a picture of a picture. This is obviously a picture. This is a picture taken with an old cell phone camera of a test tube in Boulder, Colorado. And this test tube is filled with smectic liquid crystal. And it sat in the back of some storage closet, and they forgot about it. And then they looked at it, and they see, look at all these nice ellipses. You can just see these with your eyes. No cross polarizers, nothing special, right? You can see these ellipses with your eyes. Some of them are quite large. They're all like orbiting on each other, touching each other. And actually there are lines going through them, which are almost straight lines. In fact, I'll show you, here's another picture of them from a different experiment. Here's the picture that everybody sees in the liquid crystal books. Here are these ellipses. This is a hyperbola. This is a parabola. Somehow, these smectics, which like to have equal spacing, make these conic sections. And so we wanted to understand this. Why do we get conic sections? And people can draw pictures. You can always draw a picture and explain why you get a conic section. But we wanted to predict conic sections. So let me explain to you why you get conic sections. Here, this is my green surface, but now it's blue. here I have concentric circles. And here I have concentric circles. These are equally spaced. The mountain range that gives me these concentric circles is this cone. The mountain range that gives me these concentric circles is this cone. In America, because we were afraid that the Soviets were going to beat us in space, they did beat us actually, we all learned special physics. They wrote a special book on physics called Project Physics. And everybody had, I don't know, did you do that one? Project Physics, and you have to learn. And one of the experiments you do, it's the most terrifying thing. You do it, 16-year-olds are doing this experiment, where you have a water tank, you have a shiny light, right? So now you can see the waves on the piece of paper below. And then you have a motor that's like going tap, 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 or tap, 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 right? So you have electricity and water and paper and 16-year-olds all in a room, all right? And a cranky old teacher who doesn't want to be there. And you look at these wave patterns, and you know what happens, right? If you put them over each other, you get this interference fringe, these interference patterns. But smectics are not waves. Smectics are solid materials. And so instead of having overlap, what happens is they stop growing. So you imagine here's my layer, here's a layer, here's a layer, but these layers crash into each other on this red line. So here's a red line where the orientation of the layers jumps discontinuously, but the number of the layer is the same. So, you ready for this? The molecules, they're birefringent, remember? Those birefringent molecules? If the dielectric tensor has a discontinuity because you don't know which way the molecules are pointing, it scatters light. Right? You scatter light by having discontinuities in the dielectric tensor. That means that if this were an experiment, I could see this line with my bare eyes. Because it's a place where the dielectric constant has a discontinuity, a jump, but the layers don't do anything. The layers still work. So I would see this, no polarizers, I could see this with my bare eyes. So this is focal, because you can see it. Now, you can see something else in the blue layers, which you don't usually see in the surface, which is this red line is really a hyperbola. Because when you cut a cone with a plane, you get a hyperbola. But when it projects, you just get a straight line. But that was just because I drew two mountains that were the same height. Most of the time, two mountains aren't the same height. And when two mountains aren't the same height, here's a tall mountain next to a short mountain. When they crash, you get this red curve, which is a hyperbola, and it projects onto a hyperbola. And why is it so sharp? Because my surfaces, my mountains have to have 45-degree slopes. I wanted to have 45-degree slopes to have equal spacing. So here's a structure that's equally spaced, and now you have these set of circles and these set of circles, and they intersect on a hyperbola that would scatter light. And you would see it with your eyes. So that's cool, because this is what those guys in the 1800s figured out. Right? In the early 1900s, late 1800s, they said, if we're seeing conic sections, it must mean that this is some sort of bad packing of equally spaced layers. It's just like amazing that they could figure that out without having, X-ray scattering or, STM or AFM or anything like that. It was just pure thought. And we realized that, in fact, there's an extra simplification. So I could draw this equation of the cone as phi squared equals x squared plus y squared, or I could choose to write it in this funny way where I write something equals 0. And there's a whole set of transformations, Lorentz transformations, that are invented to preserve these cones. These are light cones. If you think about what this is, there's a flash of light, and then the light goes out along this light cone. And then when I look at different times, I look at 0 seconds, 1 second, 2 seconds, 3 seconds, I get these level sets. Now, if you do a Lorentz transformation of a cone, you get a cone, not so interesting. But if you do a Lorentz transformation of two cones, here you have 2 points, and they're space-like separated, and they're exactly at the same time. And you make a Lorentz transformation, and they're still space-like separated, but they're at different times. And so you make this Lorentz transformation. This pattern here and this pattern here are exactly the same pattern, just viewed by different observers. Now, you might say that's kind of dumb. Nobody does look at crystals, at relativistic speeds, right? It doesn't come up. But that's not really the point. The point is that to go from here to here is just a linear transformation. The Lorentz transformation is a linear transformation of the coordinates. So if I want to calculate something in this system and understand something here, I can always say, oh, but really it looks like this. And I can make that linear transformation to figure out what the structure actually is. Now, it's not so useful for, it's a little useful for hyperbolas. What about ellipses? Remember all those ellipses I showed you? Here, I have a volcano. This volcano is made of an up-pointing cone and a down-pointing cone, and they intersect. There's one vertex here, there's another vertex here that you can't see. It's the top of this cone. These two vertices are time-like separated at exactly the same point in space, and you do a Lorentz transformation, and the cones get shifted, and the intersection of the two cones is an ellipse. So when the plane intersects the cone, you get an ellipse. And you can see there are circles on the inside. They are the level sets of the volcano, the caldera. And these are the level sets of the volcano on the outside. And they match up perfectly along this red line. But the red line has a discontinuity in the orientation, so you can see it with your eyes. So these guys, Friedel in particular, back in the 1900s, figured out, oh, well, these ellipses I'm seeing, it must mean that I have a layered system. Right? That confirmation came much later when people were able to do X-rays and see that you actually had a layered system, when they understood Bragg diffraction. But he figured it out just by thinking about the geometry. Yes? Oh, hi. Okay. And under Lorentz transformation, you can go from the volcano to this thing, or from these two mountains to this thing. There's another set of transformations. They're called the special conformal transformations. We don't usually teach them because they mess up, what's that called? Causality, right? They mess up time reversal. But it doesn't bother us. We don't have time. This phi thing is just, it has the same mathematics as time, but it's not really time. It turns out all four of these structures are, by a linear transformation or by a conformal transformation, related to this volcano. You can go from this to this through just a series of transformations. So that's nice. If you want to calculate properties here or understand the structure here, there's actually a frame or a set of coordinates where it looks very simple, just like that. So that's useful when we want to go back and analyze energies. Remember, I never calculated the energy before. But now I want to calculate the energy and see what the structure is. Now, let me end by explaining to you this structure, because this structure is a little special. Here I have an ellipse, and I have a hyperbola that goes through it. And I can tell you the hyperbola is perpendicular to the ellipse. The hyperbola goes through the focus of the ellipse. The ellipse goes through the focus of the hyperbola. They're called confocal conic sections. And you can actually fill them in with layers. Like this. So here's a Mathematica version. Here's this. There's a set of lines here where there are cusps, and here's another set of cusps. Let me show you what this looks like. You can take this, and you can take a giant sphere of concentric circles, or concentric spheres, sorry, and you can cut out a cone, and you can reinsert this if you wanted to. And you can actually take a sphere and have it assemble into many of these things, and I have a picture of it here. So this is a solid sphere of smectic, and what happens is these cones come out, and they replace nice concentric sphere pieces with these concentric torus pieces. And let me draw a picture for you of what that is, not here. This is the set of concentric tori. These are actually called Cycloids of Dupin. These are equally spaced layers where the cross sections are all circles. they degenerate onto an ellipse, and they degenerate onto a hyperbola. But there's a special frame to study these in. I can study them here. This and this are Lorentz transformations of each other. And so I can look at this structure. What is this? This is a donut. You take a donut, donut, with a hole, right? And you dip the whole donut in like chocolate, okay? They have that at dinner, right? You can do that at the dinner buffet. They have, right? Isn't that true? Or maybe it's the lunch buffet. All the kids are doing it. You dip this donut in, you pull it out, and now it's a thicker donut. It has a nice uniform layer of chocolate. We have to do it in zero gravity. You'd have to apply it to a space shuttle experiment to do this. And then you do it again. And you do it again. So each time you're making a thicker and thicker donut until the hole fills in. And the hole fills in and you get this little belly button, right? That is a place where there's a singularity. That's a place where the layer normal is singular. That's why it scatters light. Alternatively, you could take that donut and you could have started and you could have dipped it in acid. You dip it in acid for 3 seconds. And you do it again, and you do it again. And you would eat away the donut until you got down to this central circle. And that, too, is a place where you don't know which way the molecules are pointing. And you can see that. So you get this circle and this line, straight line going through it. And if you do a Lorentz transformation, just a linear transformation of that structure, you get another equally spaced structure, which has an ellipse and a hyperbola. So these things that you see, that these guys saw in 1905, they were actually doing special relativity back then. They didn't think of it as special relativity, but we do now, because that's what we learn as physicists. And so let me end by thanking you for your attention. Here are the people I worked with. Brian and Gareth and Sabetta were essential. And Apirity and Marcelo and Dan, they're the ones who really taught me how to think about more than one defect at a time, really complicated things. This is like the Gore-Tex core. So thank you for your attention.
So you have somatic, and you have that I would say surface function phi.
Yes, yes.
So is that A equals to the length of the rods?
Sure.
And then if it's stretched, and then we see the projection of the three level sets.
That's exactly right.
Then we see the periodicity. Maybe I can answer your first question. The periodicity, does it equal to the layers of the somatic, how it packed?
That's right. So the periodicity, this is what Elon guessed, right? The periodicity is the molecule size for the smectics. So that's what's so weird. In a smectic, you can't see the layers optically at all, right? And so that they realized there were layers was just, pure thought, an exercise in pure thought.
Then question comes out. So what's the scale of the molecules?
1 nanometer. They're really small.
Then it means the liquid crystal, each molecule itself is like a lens. It magnifies its size and projects it.
That's right. So okay, that's exactly right. Let me remind you of something that's amazing about glasses. You see glasses? You know what's amazing about glasses? You have these objects where you have 1 centimeter scale curvature, and you're managing to manipulate things that have 500 nanometer wavelengths. Right? There's this huge disparity in scales, and if it were not for diffraction, is that what it is? Diffraction? If it were not for diffraction, you'd be able to focus X-rays with your glasses. Right? The length scale of the wave, of the periodicity, has nothing to do with the structure of its cusps, right? And the structure of its focusing. That's exactly right. Smectics don't have diffraction, so they don't have this problem like light does. Does that make sense?
Yeah, that makes sense.
Yeah, so the length scale doesn't matter.
Okay.
Right? All these structures are independent of the length scale. It would be true with micron-sized rods as it would be true for nanometer-sized rods.
A special kind of liquid crystal called the blue phase liquid
Yes.
crystals.
The last couple of years, there are quite a lot of interest in turning into display applications.
Yes.
Well, I don't understand that nature of the crystals. Can you tell us what is so special about it and why that, one is that the response time is very fast.
Yes, so all that's true. I used to have a picture of one, hold on. All right, this display, this blue phase display, right? I think Samsung built this. I think it was Samsung, right? And so here's the thing. When you make normal liquid crystal displays like I showed you, the orientations were, the twisted pneumatics, the orientation mattered. You had to make sure the molecules were aligned on the top and the bottom. In the blue phase materials, you don't have to do that. You're able to not have any alignment, right? And the change in the color has to do with changes in the orientation, but they're more subtle than having to go from pointing like this to pointing like this. Regular liquid crystal displays are slow because the molecules have to reorient, right? Here it's not, it's less fluidity. They're more easily changed. However, this picture that that she's showing you, you notice that it's exceptionally blue. You notice that most of this picture is blue. It turns out that the blue phase liquid crystals displays all are kind of blue. They kind of make everything a little blue. So the examples they show you always have a lot of blue, so that doesn't bother you. Right? And obviously they could try to adjust it, but they all have a kind of a bluish haze, just like there are those special windows that,
But that is controlled by the color filters.
That's right, but the light that's coming through is made a little blue. It's not white light that's getting through. It's tinged a little bit. It's a little bluish, right? So yes, they have talked about this. But you notice that this one's 15-inch, and you can now get a 90-inch LCD one, right? Which is just a regular twisted pneumatic. So they're hopeful that this would be some new technology, but the old twisted pneumatic technology is quite sophisticated now. Yeah.
One more question. In terms of application, the Smectic liquid crystals hasn't really found, major application in display.
No, that's not true.
That's not true?
It turns out that a variant of the Smectic liquid crystal, I can show it to you.
I thought that because the response time is very slow.
Okay. There's a small variant. In the Smectic that I told you about, the molecules were pointing along the normal to the layers. But there's another kind of Smectic which is tilted. All right, so the layers are like this, but the molecules are all tilted over. And it turns out that it's very easy to rotate that tilt direction. Very fast. Megahertz, right? And so you can actually make bistable liquid crystal displays where you don't have to put a field on if you want to keep the pixel in the same direction. So they make these displays now where the molecule is stable. The surface alignment is stable, stabilizes the liquid crystal in two different directions. And you apply a field, you switch it, and then you don't need to apply a field anymore.
So how do you do grayscale?
Because you can switch at a megahertz. So you can do grayscale by fooling your eye. Because your eye is only like, what, 30? Exactly. Your eye is only 33 frames a second or 60 frames a second. So they can do grayscale. They actually have displays, they built them, which do grayscale, 8-bit color, 8 bits in each color, grayscale, or RGB scale, just using this multiplexing. In fact, it's really brilliant. I have to tell you, I'm sorry. They have a mirror. All they have is a mirror. And the mirror is coated with this Smectic bistable display. And then right above your eye, so you imagine looking into a viewfinder, right above your eye, there's a red LED and a green LED and a blue LED, and they swipe them like this, and the thing just reflects back, red, green, and blue, right? And it's multiplexed, and it makes a color image in your eye. And of course, it does video because it's doing video anyhow. So they built these. A company called DisplayTech built these. They were used for a while in the viewfinders of digital video cameras. But those have kind of gone out of fashion, right? So it was limited use. They're also used in projection displays.
I think, unfortunately, liquid crystal can go old-fashioned sometime.
Someday.
Someday,
Yeah.
Your title is Softest Crystal.
Yes.
So does that mean the Symmetric Phase is not a fluid, but has a finite shear modulus?
Well, it has a shear modulus in one direction. Yeah, it has a finite. So if you have the layers like this, if the Jolly Green Giant came to this building and pushed up the floors on one side, all the floors on the other side would move up. Right? So there's a shear modulus in one direction. Right? But one of the reasons I say it's so soft is it also enjoys, the real materials enjoy these disclinations, places where the orientation's messed up. You know, those configurations that look like bullseyes. Real crystals, that would just be impossibly difficult to take a real crystal and, cut a piece of the crystal out and glue it back together. The energy cost would be enormous. So they're soft for lots of reasons. And because they're so soft, they enjoy all these different kinds of topological structures that regular crystals can't.
So let's thank Randy again.